We present leveraging previous traversal point cloud map priors for camera-based 3D object detection and tracking. 3D object detection and tracking are core perception tasks in the autonomous driving pipeline. While LiDAR-based methods achieve impressive performance by leveraging precise 3D geometry and metric depth, they require expensive LiDAR sensors. This motivates camera-only methods that use inexpensive cameras. However, they are fundamentally constrained by depth ambiguity. To mitigate this issue, we propose DualViewMapDet, a camera-only inference framework that leverages a prior point cloud map obtained from previous mapping traversals of the same area. 3D point cloud maps provide accurate 3D geometry, which can enter object depth relative to nearby static structure, such as the road surface or curbs. Given multi-view RGB images and the current ego pose, we first retrieve a local static point cloud map patch around the ego vehicle from a global map built offline from previous traversals. DualViewMapDet uses a dual space fusion strategy. First, we project the point cloud map into each camera view and build multi-channel perspective view map encodings. These encodings are processed by a lightweight point cloud map encoder and fuse with image features in the perspective view. Second, we encode the retrieved point cloud map directly in bird's eye view using a sparse voxel backbone. The perspective view fuse features are lifted into bird's eye view and then fused with the bird's eye view encoded map features in a shared metric space. Finally, a transformer-based detection and tracking head decodes 3D boxes and object tracks using both bird's eye view and perspective view features. This slide highlights the main effect of the map prior, namely improved 3D box localization. On the left, we show the mean average translation error on the Argoverse 2 near-range setting. Compared to far 3D and sparse 4D, DualViewMapDet substantially reduces the box translation error. This is important because the mean average translation error directly measures how accurately the predicted 3D box centers are localized compared to the ground truth boxes. Here we show the 3D object detection results on Argoverse 2 within a 50-meter range. DualViewMapDet improves both primary detection metrics compared to strong camera-only baselines. Compared to sparse 4D, we obtain an improvement of about 2.3 composite detection score and 2.1 mean average precision. On the right, we show qualitative results. At the top, the prior point cloud map is projected into the perspective image, where it provides sparse but accurate depth cues aligned with the camera view. Next to it, we show the prior point cloud map in bird's eye view. At the bottom, we visualize 3D object detection predictions both in all camera views and in bird's eye view. Predictions are color-coded by class, while ground truth boxes are shown in gray. The detections are generally well aligned with the scene structure and the ground truth boxes. Finally, we evaluate whether the same geometric prior also benefits 3D multi-object tracking. DualViewMapDet achieves an improvement of about 2.3 amota compared to sparse 4D. This indicates that better 3D localization is also beneficial for tracking, since more accurate detections lead to more stable object trajectories and more reliable temporal association. By fusing prior map information in both perspective view and bird's eye view, the model reduces depth ambiguity, improves localization, and achieves consistent gains over strong camera-only baselines without requiring LiDAR at inference time. Compared to sparse 4D, we observe that our method DualViewMapDet yields tighter 3D box localization and more precise box predictions along the depth for both distant and close objects. Objects, such as cars or pedestrians, are aligned more closely with the lane and scene layout. This supports our quantitative finding that leveraging prior static geometry reduces depth ambiguity and improves 3D box localization. To foster future research, we release our code on the project website. Thank you for your attention.